Please start.
Okay. Thank you for giving me a chance to talk about this paper. This paper is collaborated with Professor Feng Yilin. He's also in Taiwan. And this paper is about quantum energy teleportation in two-dimensional quantum field series. So I expect most of you don't know what is quantum energy teleportation. So first I will introduce what this means. This is a topic in the quantum information series, but it is easy to understand. I think in the following slides you will understand what it is. To do this task, we will need to know how to construct a Merriman operator in quantum field series. This is also difficult to construct the quantum field series. In the acting field series, actually we have some method to construct for example, the scalar field series. We can construct the observables or Merriman operators by the wire operator or other operators. But in acting field series, it is actually quite difficult things to do this. Then I will introduce some properties of this operator. And finally, I will talk about the protocols in two-dimensional quantum series. Oh, sorry. So the motivation is just to study the quantum entanglement in the quantum field series. To correct the entanglement is the key point of the quantum task in many quantum tasks. To correct the entanglement, we can deal with the state and define some physical quantities. For example, the entanglement entropy or radiant entropy or other quantities. This is a hot topic recently because in the ADS-CFT, the entanglement entropy is related to the minimal surface in ADS. And this had many studies recently. But there is another character of the entanglement is that it is defined on the layer of the operator. So in this paper, we try to construct a Merriman operator and discuss the quantum energy teleportation. The difficulty to construct a suitable Merriman operator in quantum field series, the first thing is that you usually meet with the UV divergence in the quantum field series. And some quantities, but we want to define some quantity, for example, the probabilities, it should independent with the cutoff. So it is difficult to satisfy how to recognize the operator and define some independent quantities. Quantum energy teleportation, in simple way, can be described by the following sentence. The quantum task is quantum task to teleport energy to distant place by LCC. LCC means local operation and classical communication. The protocol of quantum energy teleportation is proposed by Alta in this paper. We can describe it in the 5 steps. The first step is LS and Bob. They are cis-like and they share an entangled state. And the second step is that Alice make a measurement and gain some readout alpha. We know in the quantum mechanics, the readout in measure is not decided. It is have some property to get some alpha. So any times you measure the readout is maybe not same, but the probability is fixed. This is the local operation of Alice. The third step is that he tells the readout to Bob and via classical communication. For example, with telephone or to other ways to tell Bob. This is classical communication. And the fourth way is that Bob performs local unitary operation according to alpha. The key point is that he performs the local unitary operation is related to alpha. And the final one is that on average, if we can choose some suitable local operation, that will give you extract some energy. So this step and this step is local operation. This is classical communication. So why it calls teleportation. So So in QFTs, actually it is similar in the quantum mechanics. For example, we assume that Alice is located in some region A. It makes some measurements. Measurements in quantum mechanics can be described by a positive operator valued measurement can be described by a positive operator like this one. This A means that this operator is located in some region A on some state. This is the post-main state, this is the probability. And we can also calculate the injector energy like this one. On the other hand, Bob looked in some region B. He make a unitary operation, UB at some time t. T will assume that it should be larger than the distance between them because they should make classical computation. So the time should be larger than their space-time, whereas space-like time, space-like distance. Consider the time evolution. The state will become this one after Alice get result is okay, and time evolution, and Bob makes some unitary operation. Then we can also calculate the Bob's the energy. Then the energy Bob can extract is defined like this one. If it is smaller than 1, smaller than 0, then the quantum energy calculation fails. Otherwise, it's success. We may wonder what is the role of Alice. It is important. This is because the positive of a working state. Because we for any local operation U, the energy should be larger than 0. It means that the Bob will put some energy in the quantum field series. This can be understood by the relative entropy. The relative entropy, if we define the state vacuum and the state U works on the vacuum, then the relative entropy of this quantity should be larger. This is what Hamiltonian. This is the inherent entropy. This is what Hamiltonian actually leads to the energy change of this subsystem by some fixed quantity, positive quantity. And by unitary operation, the variation of the inherent entropy is 0. And this means that delta should be larger than 0. So Bob can extract energy from the vacuum if there's no Alice. What Alice is importantly is that first they inject energy and the fixed state of Bob at the same time because they are independent. If it's not independent, then this is not possible. So we can get these two conclusions. Firstly, that Bob can extract energy larger than Alice. The second, independent is very important. We will construct the positive vacuum-like operator in the CFT. The positive operator value measurement is difficult to construct in the interacting field series. Our starting point is just from the OP block of 2-point fractions. This is 2-point fraction can be expanded in the OP block like this one. This is control block is common constant. The 4-point fraction can be seen as the 2-point fraction of the OP block. Those that this OP block is non-local. It is related to x1 and x2. So this is the definition of the component block of this 4-point fraction. Pk is just the 2-point fraction of this one. U is cross ratio. In 2-dimensional CFT, the universal form of component block of the pyramid operator is like this one. This is the hypergeometric fraction. Hk is the component dimension of this operator of the key channel. Key channel component dimension. So in this limit, we can say that this is cross ratio of the holomorphic part. This is the anthropomorphic part. This is will be divergent. And on the other hand, we may write when z and z bar is equal to 1, we will have this one. This formula actually is very similar as the probability expression of POVM as we saw in previous. So motivated by this 4-point fraction, we introduce the side of POVM-like operator of this one. This is related to the OP block, and this is ZZ bar approach to 1, this is the probability related to this. We can check whether it is satisfied some relation. First, the probability is just decay. And the second, that it satisfies the relation. This relation, the QAM operator as a measurement operator, it should satisfy. And finally, the post-Mayer state is just like this one. So we have questions. Are these QAM-like operator really a QAM? Actually, this is QAM-like. It is really not the real QAM. It is because that the QAM operator should equals to the identity. But here, right, we say that it's not equals to identity, but the expected value of the vacuum in the vacuum state is actually 1. So in the vacuum state, it is satisfied. This is enough for our purpose. And the question 2 is that, are they local? Yes, we need to say that the OBE block can be run this one, but the more useful formula is that you write in the Smaring expression of the OBE block. This is the kernel. This is the primary operator of the key channel. And the DA is just the Cauchy domain of the interval A. And this is the expression of the kernel. This can be derived by the channel operator permutation. We can check this OBE block. First, we can check the 3-form function. It is universal, and we can produce this. And also the 4-form function, and it is also universal. We can also get this one. The second non-trivial check is that is their causality, because in this X1, X2, in the Cauchy domain that we expect the operator at the point 3 should communicate with X1 and X3. This is by the causality argument. And then we can check that the OI can be expanded as the OBE block. So this is an operator equality, so we expect this to satisfy. Actually, we can check the indeed Smaring from the OBE block. It do satisfy. Even though that in 1 and 2 region, they are communicated with the operator, but in 3 and 4 region, they are not communicated, but they cancel with each other. As you can see in this. This is in 3 and 4 regions, not non-zero, but these two contributions is there. Actually, we have seen that there are UA divergences in this in our construction, but it is easy to do to regularize this one, just like this one. This is done by similar as regularize the boundary state by Cardi or the localization of Tadasi. So this divergence appears is because this is should relate to the cutoff usual, and we can define the regularized QAM-like operator by this operator. In two-dimensional, we can construct like this one as a local in some interval x1, x2. A make measurement is described by the QAM operator we have constructed. The injection energy actually we can calculate as this. Bob is located in some interval x3, x4, and his unitary operation is just this one. This is eta k is some feedback control parameter. Theta is some dimensionalized parameter, which is assumed to very small for calculation. And the GK is just, we choose it like this one. Fx is the Smaring fraction. This is positive maybe. And this is the unitary. Can we check that this is the emission? So Bob will make the operation at time t. And we have said that after consider the time evolution and the unitary operation, we will get the expression of ET. And finally, MC is just definition of the time evolution of this MK. And if we assume that the theta is very small, so we can expand it like this one. So finally, we will get a way out. We want to define the EP of Bob's extract energy. So it is just related to the communicators and some communicators. This is, as we can see, that MC is just related to the parameter operator. This is 3-bound function. This is 4-bound function. If you, in other terms, it's actually the high-bound functions. The problems can be reduced to calculate a series of correlation functions. Since we can use the communication of the Hamiltonian with the operator, it is just can be used the Hasbro equation. We can get it just some correlation functions. These communicators can be obtained by analysis continue from the Euclidean operator having a derivative. Just show the results. Before we show the final results, I want to discuss the direction to go if we cluster of the correlator. What do we mean cluster? It means that if we find the expression of EB, we can see it is related to the T and the theta. So the general form of EB will be like this one. This is in any terms it is expanded by theta, and then we can expand it by T when T is very large. So the cluster of the correlator means that the T to equality. So this contribution is 0. We mean this limit is cluster of the operator. When the goal means that this quantity must be negative. We will show why, and we will show the physical explanation of this result. We can just say that the first of theta, it is just of this one. So this is just 1-point function. It is 0. It is as expected. The second order theta, it is related to the 2-point function, and you can see that it is all square. The pk is also positive. So this quantity, the sign is decided by the commutator. The definition of commutator D2, we will see. The calculation actually showing the sign of this commutator is not easy, but when we do in the Fourier space, we can show that D2 is just an expression like this one. This is Fnh is just the coefficient of the Taylor series of this one. You can check that it is always positive. And this is positive, this is positive. So finally, this term must be negative. This because there is a minus sign here. So why? Because in the latitude limit, the effect of the Alice measurement is vanished. We can see in the previous expression, or we can sort that when the time is very long, so the effect will approach to the infinity, so there's no effect actually X. If the bulb make a unilateral opening without Alice, as we have mentioned that in the latitude limit, it will just approach this quantity. As we have shown that as a positive of the vacuum, this quantity must be positive, so EP must be negative. This is why in the cluster limit, this will must be negative. This can also be understood like that. If we cluster two operator, this implies that the state is more or less the product state. So there's no entanglement in these two parties. So this also suggests that entanglement is very important to the success of the quantum energy calculation. Next, we can calculate the next leading contribution. As we have shown that this is, if we just see the first order theta, so this is 0, so we can just see this term. Some leading correction is just calculate the 3-pound fraction of the operator and with some integration. The calculation is completed, but the reality seems very not too analytic. We can get the final result as this one. This is definition of this quantity, and we have assumed that this quantity is positive integral, and we note that nkt, this term is related to beta k. Here, beta k is just some parameter to control the sign of this term. So in this way, we can always ensure that if we choose suitable beta k, then we can get EB is larger than zero. Larger than zero. This means that we can gain energy of Bob can gain some energy by his unitary operation. So after a summary of this, we mainly use the OP block to construct the state of PWM-like operator in the vacuum state of 2D ZFT. Actually, the construction is only useful in the vacuum state. For general constructions, it is still unknown, and maybe we may have further studies on this topic. And these operators are smiling form in the cost domain of an interval in 2 dimensions. And this fields in the Higgs dimension. So in Higgs dimension, we actually have this way is field. So we should find other ways to do this. So if ignoring the correlations, we have shown that the quantum energy teleportation is mass fields. This is show the importance of the entanglement for the quantum energy teleportation to be successful. And if we consider the correlations, then the quantum energy teleportation can be a success. Okay, thank you.
Questions or comments?
Are you able to discuss, for example, like the efficiency of this protocol or the speed of transfer of the energy using your set of the OVM? See if you have some characterization about optimal set of the which allows the maximal efficiency in the transfer or the maximum speed of transfer, this kind of thing.
Actually, this calculation is, in some sense, it is related to the cutoff, and the input energy is very large, but the extract energy is very small. And we just consider the large T limit, so we can't say which is maximal, which situation is maximal and which situation is minimal. I don't know this answer. And the important thing is that the quantum energy teleportation actually it depends on the PWM you choose. So in this case, we just choose the special set of the PWM. Maybe you choose other ones, it is better than this one. So maybe I don't know the answer.
Any other questions or comments?
Thank you, you are still here. Thank you, Mars. Thank you.
Okay, if not, let's thank speaker again. And we have just finished all the program today. Let's thank all speakers today again.